So, in sense of new ideas, today's meeting is absolutely useless. If some of you, well, everyone came, but if some would not come, you would not lose anything in your fundamental education. But the whole course is not possible without this meeting and previous meeting. So those are technical efforts that are absolutely needed to arrive to the last stage. And those steps which are simple or zero from the point of view of ideas are absolutely necessary to arrive and understand the quantum dissipation that is our target. So we are targeting to predict the quantum dissipation of quantum systems, and through the course we agreed that it will be based on perturbation theory of interaction between system and path, and we already covered that based on the average over ensemble one is getting dispersal, relaxation, losing of phase, dephasing, right? And based on the fluctuations of the transition rate by fluctuations inserted into the way how the system transfers from ground to excited state, we get the longitudinal relaxation. The stochastic oscillatory random noise was good in sense of giving longitudinal relaxation in principle for two-level system coming into the center of the Bloch sphere, but the shortcoming was that it was not following the detailed balance. It corresponds only to infinite temperature, and we need to include zero temperature and somewhere in between. So for this reason, we assume that the system of primary interest, which we think of as a two-level system, is coupled to infinite number of resonant oscillators. They all have the coupling strengths. So and there is a bilinear Hamiltonian. Then we removed counter-rotating terms, keeping only slow terms in the Hamiltonian, and took the step of projecting dynamics of overall density matrix of the world onto density matrix of the system of interest, which is symbolized in the operation of trace. So integrating out all degrees of freedom related to the path degrees of freedom. This, in case of bilinear coupling and path in a thermal state, we plan to obtain combinations of creation and annihilation operators of the path, which will give us a number of quanta in the thermal reservoir, which do depend on the temperature. And through this connection, we will get temperature-dependent relaxation, including both dissipation of energy and acquiring accumulation of energy from the path. So spontaneous excitation from ground state to a little bit higher, right? So in some sense, we just observe the mechanism, how the system is coming into thermal equilibrium. So statistical thermodynamics assumes that everything is thermal equilibrium, and here we are considering the way, the time dependent, the path, how the original non-equilibrium system is approaching thermal equilibrium. All derivations are absolutely impossible to fit into one meeting or in 2 hours, so we chopped them. Most philosophical ideas and steps were introduced last time and will be finalized next time on Thursday, not 2 meetings ago. Last time we did already stickers, right? Correct. Today we will do big stickers. So basically, This is equation that you have completed as part of your quiz, and we did together with stickers through the projector, right? With your help, I'm going to fulfill the same assignment today, and then we will do one more step. We are going to open brackets in this equation and get to the next one. So it will be assignment for the whole meeting. As soon as we fill the next board with stickers and signs, pluses and minuses, we will have additional 5 minutes to identify terms that would cancel, and then we will be done for the day. I hope very much it will take much less than 2 hours. Well, not much, less than 2 hours, but it will be kind of logical termination. To fit everything into one meeting is impossible, so we'll better chop that onto sections. Anything I missed or anything we need to, you wanted to ask last time, anything we need to discuss before starting intense activity on gluing stickers? Or everything you either don't care or everything looks logical? So, what is the pattern of filling these stickers? So I believe the parts of the bilinear Hamiltonian are coming 2 times. Once with time t prime and another with time t. So it's something like t prime t. Then here it is t prime, and here it doesn't matter in which order, t prime t prime. Those can be swapped because they are they differ only by order of this part of the Hamiltonian. So those with t are sine, those with t prime are so I'll take the pleasure of gluing it here because you all did it in your quizzes. And when we come to opening brackets, each of us will have enough letters to paste the stickers. So considering the assignment that you just agreed or were not protesting, I wonder which of these equations you it's in typing in the Microsoft editor. So the idea, well, it's not the idea, but just an attempt to live with necessity to do so many stickers. Like, why do we need Hamiltonian in second power? One motivation that we discussed was that the first order perturbation gives 0 contribution, therefore one just takes the next one, the second order, and we do have so this equation is nothing by second order perturbation theory. apply it to the density matrix of everything of the universe, and then we just trace, integrate out all the path. Another view on why the second order is needed can be related to the noise that we covered, classical noise in the labs, and classical noise is also part of the subject that Tori has bravely selected. The Benjamin equation, it is how the generally any system, but typically people apply it to harmonic oscillators or maybe free particle evolve in space and time under random noise. And I was just trying to look into Wikipedia what it tells about Benjamin equation, and it tells interesting thing. So I'm telling noise irrelevant to the subject, just comments. They write Newton equation of motion with a friction and with additional term which is proportional to force, which is random. And the force is so random that it gets positive and negative. And if one averages just an equation, it gives no effect. But if one tries to find second order observables, something like mean squared deviation, like x squared, or kinetic energy, which is velocity squared, then product of two random forces becomes a correlator that gives non-zero contribution. So it's something that gives there is an analogy. First order doesn't affect, but second order things do some job. Maybe at one point you can cooperate with those who took this course and design a course of quantum relaxation for kindergarten. Telling like you take so many pink, so many cyan, and just paste it in the alternating order, and one calls it quantum relaxation. So if one would try to do it by regular writing, either in a notebook on the board, there is a very high chance of human error. Just because, so its ideas are not very many, but by rewriting stuff again and again, one can mix many things. So it is a task for a very sober person after a lot of coffee. What is interesting in this expression is it did came out as practicing of the two commutators, right? And it is why we got minus signs, and it is why the density matrices come in different place. The path density matrix is always last. And the system density matrix in a different place. Each time, so those things are written as a column, but it is a little bracket, so it is a summation of two terms. Each time we open brackets, number of terms increases, and by looking at not being much waked up, I had a first thought like, oh, there are so many terms because there are counter-rotating terms in Hamiltonian, but no, you already removed them. So if one would include rotating terms, it will be more. It will be almost undoable. we have the raising for electronic system and lowering for bath, or lowering for bath and raising for bath and lowering for the system. And frequency of the system, omega, and frequency of the bath in UK are coming always with subtraction, which is a consequence of rotating wave approximation. We assume that they are nearly equal, and this phase accumulation will be close to zero. We just need to have everything accurate. We need to keep it. And by integrating over time, we noticed in the when we covered the time dependent integration theory, the first order, right? We got similar expression, integral of oscillator exponential, and then it converts into function that gives us frequency selection. It will be like function that maximizes when resonance condition is fulfilled. It is a good approximation for the delta function, and we were calling it sinc function, right? Like sine of the time and frequency difference divided by time. And if the limit of time equals zero, it is as good as delta function. I'm just trying to look forward and interpret what we can get out of it. So upon integration, summation, there will be some resonance conditions. Okay. Right now, each term, each colored term has only linear power of the bath operators, right? But the plan is that by multiplying two different colors, we will. So the operators of the two operators of the system will be not affected by the trace operator. So after we arrive to our final result on coming Thursday, this product of like sigma plus sigma minus will stay there. The terms sigma plus, by the end of the meeting, there will be reason to cancel them. So it will be still less terms. But in each term, we will have product of two bath operators, like annihilation, or annihilation creation. And those pairs of bath operators merge together with density matrix of bath, which is assumed to be Boltzmann distribution for the thermal state, right? They will give us the number of quanta in a given bath mode, temperature dependent function, which is related to Bose-Einstein distribution. So this is the only idea that we already discussed on previous meetings, and we just need to go over this boring algebra and get minimal amount of
You're not back. No idea why it's
okay. So you just need to do this algebra to the idea is clear, but the terms do not multiply themselves. We need to apply a little human effort in this. So in a few minutes or seconds, I'm going to walk towards another screen, maybe complement what is not yet written as a pattern, and then we can see that the first row on this board, right? It is a product of brackets, each of which has two terms. So 2 by 2 will be 4, right? So first line in this equation will be translated in the first line on the other board. And here we have one term with 2 brackets. On the other board, we will have 4 terms, right? So each term will have colored stuff first, and then product of two density matrices of system and bath later on. Same for the next one. And after we move there and do this early steps, I'll try to do a couple of steps myself and then invite everyone to do either one at a time and then do second round or come and do. Maybe it will be better because even this relatively simple task of opening brackets, it needs concentration, and you can come do the first thing and then sit and prepare for your next round and know what you want to do. So to have a little additional guarantee of success. Okay. So if you compare the expression at the board on the left, it's maybe ing t prime sin t. So the creative part of this assignment includes identifying what would be the sign, what would be the time, and what would be the operator for the system of interest. And everything else is here. Time dependence of the density matrix of a system equals to 1 minus 1 over h bar squared, summation over all path modes, integral from initial time to time t over dt prime. Unequal parts, unequal types. And you can verbalize the logic behind it.
Well, everything in this one is going to be, in this row at least, going to be d prime t. But this just needs, sigma plus sigma plus things that are different. So this next 20 years would be sigma minus sigma plus.
You're helping the next. Okay, and here they are of the opposite activity. Sigma minus lowers system state, and sigma plus will raise it back.
Yeah, right. Yeah.
Okay. Max, would you like to? Yeah. Pin first, sign second.
Right. So
And what do you observe? What do these operators make to the system? So raising operator converts it from lower state to higher state, and this one brings it back.
yeah. You're saying the reverse of this. Well, it's the same.
Okay, yep. Sorry, would you like to try? Otherwise, the logic of someone which the recordings and what you learn from. So what goes first, pink or cyan? Okay.
So I thought it would be double of the sigma minus because we had double of the sigma plus up here.
Okay. And go lower than what would be the result of applying lowering operator to the state that has already been lowered?
or for the bus, if you apply two raising operators, well, one after another, like if for bus it is okay, but for system, if we already brought the total system to the ground state, and we want to apply warning operator once again, what will be the result? Okay, so likely this term will disappear because of this reason.
Yes.
Okay, yep. Teresa, would you like to try?
So what was first, pink or cyan?
Cyan,
Okay,
down first.
what is the sign in front of this term?
Sorry.
If you
This negative.
yes, please put minus sign. Excellent. Yeah, thank you. Okay.
So it's gonna be cyan, pink again. And it's gonna be plus minus. Thank you.
Oh, yes.
Right here.
Okay. So we had forgotten to cover it
Yeah.
in previous.
Oh, wait. Yeah.
Okay, yeah, thank you. So this minus sign comes because you just inherited from previous one. It comes from commutation. And what is your opinion? Will this term stay or disappear?
It's sustained.
Okay, yeah, thank you. Stay or disappear. Will this term stay or disappear? What is your expectation? Or if there are two.
No, that's weird.
Okay, yeah, thank you. So what will come first, pink or cyan? Cyan and this term comes from commutation, right? Would you expect this term to stay or to disappear? So operators, weather operators for this pseudo spin, are they the same or different? of sigma. Sigma has both different same. So if there's the same, there is a chance that it will disappear. So it's better if they're different. It has higher chance to survive. Okay, yeah, thank you. Steven, would you like to try? First spin is prime. So why there is sigma minus here? How do you decide that it is minus, not plus? I believe you did correctly, just for the next generations to do with our teaching.
Well, the simple logic is that it's
Or one can follow with plus, 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 minus, minus, minus.
Yeah.
Okay. Or one can simply open brackets and have everything that if first terms is the first from the first bracket sigma plus, then you have first and second from the second bracket. Would this term stay or get removed if you have different directions of the operator? Okay, yep, I would think so. And what would be the sign in front of this term? Okay, because of the limitation. Yeah, thank you. Okay, now we come to the second round, which is expected to be substantially weaker. Okay.
Sounds like you want to go next.
Perfect. You can follow David into the angle. Okay. So, same. Any other comments? Okay.
But I have a thought question because one way in the last class we were talking about how operators affect spin and
Mhm.
So I don't see like when you say it's gonna like you're classifying it as a spin instead of octal because when Dr. Kalina told us about raising operator octal, she said that it depends on the you have you can raise you can
Recording in progress.
to lower
Recording in progress.
like you can lower the system like we should imagine like a system like when you have an orbital has 4 steps, you could lower the steps, you can keep lowering it and it will not give you 0. It's a lot of fast. Like talked about speed, I'm talking about all the things that you could apply a lowering operator on a system that has, we should imagine like a system that has like a 4 ladder and you can keep lowering.
Here we have only 2.
Yeah, that's what I'm saying now. Why do we think it's 2? Is it because it's a 2-level system?
No, we are testing our new theory on 2-level system because it is so much simpler. But one can extend it to larger number of levels and without this. The logic why this terms will be cancelled is not because of the sigma minus here. It will be cancelled for different reasons. For path operators with different indices will give 0. So it's not a reason, it is a signature that this term is going to be to cancel. I like the question. Adam, would you like to walk up? I think we're getting ready to make an outreach event, quantum dissipation of a kindergarten. Look, it alternating like chessboard. Let's give some comments. So you already put last time, did you? What about the stay and go? Would this term survive an averaging or it would be a book? Okay. There. Yeah. Okay. And it will stay, right? Yeah. Okay. Yeah. Thank you. Correct. Unless you okay. Thank you.
Just as a check, like the sigma minus is like an X on the system density and then the PX on the, or X on the bathtub range?
Yes.
Correct, okay.
Yes. Okay. Additive plus, right?
Yes. Yeah.
Okay. Yeah. Thank you. So, what else do we have left for today's meeting? One would make perform the average over bath degrees of freedom, right? So bath degrees of freedom. I'm going to give a very small comments underneath of the screen, so it doesn't justify, or maybe on the little space in the area number one. So density matrix of the bath is a product of thermal density for those cylinders. So based on this, each of those cylinders in the bath are assumed to be independent and not interacting to each other. And from this point of view, there is an interesting consequence. If one performs
Everywhere in the expression so in the expression that we processed, there are different indices k and k prime, and if we try to average for past degrees of freedom for to be correct, one needs to put past here, row past here. So if these indices are not equal, this can be treated as trace over bath degree k. Bigger a plus.
there is a way to prove this statement. Here I'm just declaring them, but it is a good exercise to prove that they're correct. So it's
Taking a trace with respect to k and k prime, like wouldn't it just be the trace? Like, wouldn't you just not need that subscript there?
So since those are independent, right, we can one row plus mode, row plus mode 3, row plus mode k plus mode k prime. So trace B capital includes tracing over all degrees of freedom, but those trace of all partial degrees of freedom that
Well, only in the bath, though, right?
only the bath.
Yeah.
Yes, only the bath. So those partial modes which do not meet the Taylor operators, ladder operators, their trace gives 1 because they are normalized. They have this partition function. So we pick up from the whole trace only those which we need for this particular expectation value. So in this line, you have times trace path 1, row path 1, which will give us 1, and infinite number of terms. So we expand this one to the product of infinite product of terms. With 2 of them will be 0 and the rest of them will be 1.
Can you explain the operator having indices? Like, what does it mean? Like having, yes.
So when we did set up the Hamiltonian, we had the summation over all modes of the bath. So it means that our two-level system, so in general we want to speak about any primary system, but to be simple, we are speaking about just two levels. Our two-level system, tonic levels, are coupled to infinite number of either nuclear degrees of freedom or modes of the resonator. So in the black box radiation, right, there is a density of states, so many states at given frequency, but if one doesn't normalize them, if one just looks for the number of states in the vacuum, at each finite frequency there will be infinite number of modes. And we want to make sure we count, we look on interaction over all of them. So we represent the environment as a system of infinite number of harmonic oscillators. Each of the oscillators is counted by index k. So in the result, we make summation over all of them. So we look for average influence of each of these thermalized harmonic oscillators. Yes?
So it's just like summation of all the reason operators of the harmonic oscillator.
Different oscillators. Oscillators with when we were writing Hamiltonian, we had frequency omega or nu sub k for each oscillator, and they are approximately equal, but formally they're different. We count them different. Okay, so let's go to our main achievement of this collective effort and see what we can do with it. So here we have different. So there are several reasons to cancel terms. So one is that they belong to different modes of path, but then it will be correct for each term. We always have these pairs. Another reason that I'll better prepare solid justification and declare it when we meet next time. But just look that there is a property. Here, the path modes are of the same nature, so they are all lowering operators. It is giving my duty to confer this additional outline. So for last column, you also see that they are both relation operators, and they have different indices. But then average for thermal bath of such type of terms is expected to give zero contribution upon average of the bath. In the remaining terms, we do have true, they belong to different indices, but summation of both indices, but only in situation when the indices would coincide, which was covered in such summation, we will have expectation value of number operator, be Dagger times B or
A dagger times B, or number greater plus 1 for B times B dagger. And it is expected that we will keep twice as less terms only from the middle column, and upon performing the average over the path, where one index will disappear, raise average summation over all path modes, trace, and the time integration, we are going to convert each of these terms into system operator, system density metrics, system lowering, and system raising, where the influence of path will be kept in form of number of modes, number of photons, number of quanta in the given path mode. So this exercise will be carefully done when we at the beginning of the next meeting, and when we are done, we will perform analysis of the resulting equations that are expected to provide solution with detailed balance, both time dependent and what is the name of stationary? There is a better one for stationary state, and when one sets up that time derivative is equal to 0. Equilibrium, stationary state. Steady state,
Yeah.
yes. The goal for the next meeting is to further simplify this equation so that it will have only 1, 2 times 4, 8 terms. And each of the terms will be weighted by time-dependent factor corresponding to temperature. So these equations will have steady-state solutions and time-dependent solutions that will lead us to detailed balance. We do see some incomplete parts in processing this equation, but it's possible to try doing few next steps, but we will not finish today anyway. So it would be more logical to postpone the crown of our course to the next meeting. So I would like to announce conclusion of this meeting. And if there are any questions or suggestions, please go ahead and press. Oh. If there are no questions, anyone is welcome to walk over in the space or looking forward to see those whom we see for a class on Wednesday lab tomorrow, and those whom we see for group meeting shortly.